Question number 4. Infrared waves and ultraviolet waves are part of the electromagnetic spectrum. Part A. Suggest one method of detecting infrared waves. Well, infrared waves are heat waves. So any wave detecting heat. You could use the back of your hand, you could use a thermometer, or you could use any kind of temperature probe or temperature sensor. The back of the hand, the skin on the back of the hand is more sensitive to heat than the skin on the front of your hand. So any of them. Part B. State why ultraviolet waves are potentially more dangerous to humans than infrared waves. So when you're looking at the electromagnetic waves, you've got the visible in the middle. Richard of York gave battle in vain. Then you've got 7 waves in total. R for red. We've got infrared there. V for violet. We've got ultraviolet there. We've got radio right all the way over here. R for red, R for radio. That's how I remember that. We've got microwaves here. Right over this side you've got gamma. And here you've got X-rays. Radio waves have got a long wavelength and they've got a low frequency. The frequency is how often it vibrates per second, which is related to the energy. So over here, our wavelength is big, our frequency is small, and our energy is small. Watch. There's long wavelengths. As you come over here, the wavelength's getting shorter and shorter. Look at how much energy my fingers have got now in my hands. Going up and down a lot over here. So over here, it's a high frequency. The frequency is how many vibrations you've got per second. And it's also related. Higher frequency causes higher energy. So ultraviolet waves are more dangerous to humans than infrared. Ultraviolet is because they've got a higher frequency. Any wave over here has got a higher frequency and it's got a higher energy. So the question could also say, why is gamma more dangerous than X-rays? Or why is X-rays more dangerous than infrared? Or why is infrared more dangerous than radio? So all of these waves over here have got the high energy and they're dangerous because it could ionize your cells. More energy is more dangerous. Part C. The table shows information about different sections of the electromagnetic spectrum. Complete the table by adding the names of the different sections of the electromagnetic spectrum. Use the name of each section only once. Right. Let's roughly work out what the frequency of each of the 7 electromagnetic waves are. So first of all, let us show you a good way of remembering what the names of the electromagnetic spectrum are. We've got raging Martians invaded Venus using X-ray guns. That's what you call a mnemonic. The first letter of each word stands for the first letter of each word of the electromagnetic spectrum. R is for radio, M is for microwaves, I is for infrared, V is for visible, U is for ultraviolet, X, well X-rays is just for X-rays, and G is for gamma. Now there's not just one wave in each of these bands. There's a range of waves, but roughly the frequency of radio could be 1 times 10 to the 6. Microwaves about 10 to the 8. Infrared about 10 to the 12. Visible light frequency about 10 to the 14. UV 10 to the 16. 10 to the 15. X-rays 10 to the 16, gamma 10 to the 18. They can be longer than this, they can be shorter than this for each different wave. So they use medical scanning. I've got 10 to the 16 here, and it says it's produced by changes in the electron orbits of atoms. 10 to the 16, that's X-rays. Medical scanning, 4 times 10 to the 18, produced by changes in the nuclei of atoms. That's your gamma. Communication, 9 times 10 to the 6, produced by oscillations in electrical circuits. That's radio waves. And for communication, with a typical frequency of 5 times 10 to the 14, produced by changes in the electron orbits of atoms, visible light. Changes when an electron drops back down from an excited orbit, it gives out visible light. It can do, anyway. That's what gives you your neon lights, argon lights, things like that. Part D. The speed of light in a vacuum is 3 times 10 to the 8. In fact, all of those waves all travel at 3 times 10 to the 8 meters per second. In case you didn't know what 3 times 10 to the 8 is, it's basically a 3 with 8 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8 meters per second. It's easier if you put a couple of commas in. You can see that's 300 million meters per second, which is pretty fast. The wavelength of an ultraviolet wave is 360 nanometers. So a nanometer is times 10 to the minus 9 meters. Calculate the frequency of the ultraviolet wave. So it's told us the speed of light, which is c. It's told us the wavelength, lambda. And we need to work out the frequency. That's our question mark. Is there an equation that links these three things together? Yes, there is. The speed of light equals frequency times by wavelength. So we need to rearrange that. Let's pop it into a magic triangle. Draw a triangle, do a top shelf, and then this big section on the bottom, let's split that into 2 by putting a multiplication sign there. Now our equation is something times by something, and we've got room for something times by something, so we'll shove it in. Frequency times by wavelength. We've got one space and one thing, so we'll shove that thing in that space. Now that you've got the magic triangle, cover up what you're looking for, and what you're left with is how to work it out. So we're trying to work out frequency, so cover up frequency, and frequency is c divided by lambda. So frequency equals c divided by lambda, speed divided by wavelength, so that's 3 times 10 to the 8 meters per second divided by 360 times 10 to the minus 9 meters, and that comes out as 8.3 times 10 to the 14 hertz. Question E. Radiation from all parts of the electromagnetic spectrum is emitted by a star. The outer layers of the star absorb some of the radiation. Figure 7 is a graph of intensity against wavelength for the electromagnetic radiation coming from the star. So intensity, that means how bright it is, if you like. And that's your wavelength along the bottom. The wavelength's getting longer and longer. Describe how the intensity of the electromagnetic radiation changes with wavelength. So how does the intensity change with wavelength? Right, well generally you can see as the wavelength is going from 300 up to 400, it's getting bigger. Then at about 400 it's peaked. It sort of stays roughly the same for that section. And then as the wavelength gets longer, the intensity decreases. And you can see every so often there's these little spikes, the little decreases of intensity. Now, if we talk about it increasing 1 mark, staying steady 2 marks, decreasing 3 marks, then the spikes, we could get up to 4 marks. And it's actually only worth 2 marks. So we've got it well covered. There are several sharp decreases in intensity. That's these things where it suddenly dips down. Question 5. Figure 8 shows a ball on a slope at position P. The ball is projected up the slope from B. So basically means it's fired up the slope. Q is the highest point the ball reaches before it rolls back to P. So from P, gets fired up here, stops there, and then comes back down. Which statement is correct? When the ball returns to P, the ball has less gravitational potential energy than it had at the start. No. Gravitational potential energy, GPE, is mass times by gravity times by height. It's got the same mass, it's got the same gravity because it's on the same planet, and it's at the same height, so that is not correct. It's got the same gravitational potential energy. The ball has more gravitational potential energy than it had at the start. No, I've just explained that. It's got the same. The total energy of the whole system has increased. Nope, you can't create extra energy. That's the law of conservation of energy. The total energy of the whole system stays the same. Yep, that's correct. The law of conservation of energy. The ball has a mass of 100 grams. When the ball leaves P, it has a velocity of 5 meters a second up the slope. When the ball returns to P, it has a velocity of 4 meters per second down the slope. I guess I should put that as U, which means the initial velocity, and V is the final velocity. Calculate the decrease in the kinetic energy of the ball between leaving P and returning to P. So the decrease will be what it had at the start, take away what it had at the end. So kinetic energy equals a half times by the mass times by the velocity squared. And what we usually do is we would say a half mv squared. Now so that's a half times by the mass times by. Now if we use u as the initial velocity, then square that. And then we'll need to take away the kinetic energy at the end, which will be a half times by m times by v squared. So that's the kinetic energy at the start, take away the kinetic energy at the end. And that'll give us the difference, the change in kinetic energy, the difference in kinetic energy. Now 100 grams is 0.1 kilograms. It needs to be in kilograms. When you're working this out, make sure that you square the 5 first. Then multiply it by 0.1 and then times it by a half. So that's 1.25 take away 0.8 and that equals 0.45 and that'll be joules. All energy is in joules. Part 2. Explain why the kinetic energy of the ball decreases between leaving P and returning to P. Right, well, it goes up the slope and there'll be some friction between the ball and the slope. Now, friction causes things to get hot. So we're going to lose some of our energy as heat energy, and it'll go to the surroundings. And the answer is always the same as that. You could say that work has been done on the ball because a force has been used to move at a certain distance. And work done equals energy transferred. Question C1. State the equation for the efficiency of a device that transfers energy. Well, efficiency equals the useful energy out divided by the total energy in. Useful energy transferred by the device divided by the total energy supplied to the device. Figure 9 shows a motor pulling a box up a slope. There's a box of mass 70 kilograms. The motor pulls the box up the slope through a vertical height of 1.3 meters. The total energy supplied to the motor is 1,500 joules. Calculate the efficiency of this method of lifting the box. Well, in order to calculate the efficiency, remember we need the energy that is useful, that comes out, and we need to divide that by the energy, the total amount of energy that we put in. Now the useful energy out, when the box is being pulled to the top, the box is going to have gravitational potential energy because it's up a height. So technically we could let the box roll back down and then we could use that energy for something useful. So the gravitational potential energy is mass times by gravity times by the height. And we already know that the energy total was 1,500 joules. So the mass is 70 kilograms. Gravity on Earth, we'll keep it simple and say it's 10 newtons for every kilogram. If you do A level, it's 9.81, but for GCSE level, gravity on Earth is 10 newtons for every kilogram. And the height, the vertical height, is 1.3 meters. It's always the vertical height. Don't worry about the diagonal height. We're only interested in the work that we've done against gravity. And since gravity acts vertically, we're only interested in the vertical height. So if it gives you this distance here in the exam, just ignore it. Now let's divide that by 1,500 and that'll tell us our answer. That's 0.606 recurrent. Now if we rounded that up, that would be 0.61. And if we wanted to do it as a percentage, that would be 61%. Because to turn a decimal into a percentage, you just multiply it by 100. But it would be fine just leaving it as 0.61. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much and bye for now.